and also on Wednesday, but one was about topic and the other was about a lot of other logistic stuff. Wednesday is not a vacation day, all right? Wednesday is a school day, and you have to still do the school stuff. And she's not in this class. I'm not going to name her, but I got an email because it said everyone virtual, and I didn't say today. I just said everyone virtual because in the agenda for Wednesday, it came to this page, and instead of splitting you up as in class, you're going to do this, virtual, you're doing this. She thought that meant she didn't have to do it because she was in person. So let's make it really clear. If it's on a Wednesday, and the assigned topic is on a Wednesday, you do have to do it. Another thing, and this is my fault because I didn't make it clear. I really didn't make it clear in Needle Art. If we start something in live participation, you don't get credit for it unless you complete it. So that's why I say make sure you do this at home. You want to go back to the student-paced version and do the student-paced version and complete it. The advantage of me doing it with you in class is I can give you explanation about it. So as we go through it, but I need you to complete the assignment. So if there's any time I start something in live mode, if we don't finish it, it's on you to finish it at home in student-paced. That's the problem with Nearpod. Nearpod had a nervous breakdown yesterday. I don't know what was going on with it. The computers were all running slow here as well, but it had reset elements and compounds. I had to go back in, resave it, relink it. It should be working for you now. I had a lot of people email about that. And my early adopters, my beta testers found the problem. We worked it through. Ivy, you were immensely helpful sending me those URLs. That's how I found it. If it hadn't been for that, I wouldn't have found the problem. So we got it worked out. Everything should be working as intended at this point, okay? And is everybody okay now with uploading papers? You should all be able to have at this now, but if you've got questions, let me know, and I will show you how to do these things, okay? So Wednesday, not a vacation day. Thursday, that was a vacation day. In fact, I told some of you to go out and play, all right? I'm sending you messages. Don't take that as hate mail. Take that as a reminder that you do have something due. I do not want you to fall behind. That was what got you in trouble, some of you, in the first place. You let it pile up. And believe me, the majority of us in this room, including me, we are procrastinators. We don't want to do it right now. It's so beautiful outside. I'll do that Saturday. Saturday rolls around. Boy, this is a beautiful day. Oh, I'll do it Sunday. Sunday comes around. Oh, man, it's nap time. I know how this works, guys. I live it every day. So you got to set yourself with the mind of whatever's on the agenda to get it done that day as best you can. If you have to take it over to the next day, that's fine. But if you can get it done, great. Sometimes it looks like I'm piling stuff on you, but it's not. It may just be a website, like P-Table. It's just a resource, so you have it, you know to pop it up, you're going to use it. And so it looks like a lot of links, but a lot of times it's not. It's not as bad as it looks. And then why did I get a message about Nearpod we did in the class? I just answered that. If we didn't finish it, you will know because you will not have a report. There'll be a no submission showing up in your grades. So that means you didn't finish it. You got to get it completed, done. Now there was a problem, and I still think it was because Nearpod was having a nervous breakdown yesterday. Some people did it, saw that they were 100% participated, but what it sent to me was 0 participated. If that should ever happen to you, screenshot it, especially if the computer's running slow that day. If you're finding, like yesterday, I was about ready to throw it out the window. The network was so slow. I had a parent, I was trying to pull up some information, and we just sat there 3 minutes, 4 minutes, waiting for this thing to load up. So if it gets like that, your computer's acting like that, screenshot it And then it's okay, you're not, send it to me, I'll give you credit. But I need to see that you actually did do it. And then today it's working great, so who knows? Maybe we were getting denial of service attacks. Do you know what that is? If somebody says that? What they do is a hacker, I know Dalton knows this, so, don't overcorrect me here, but basically what it is a group, either an individual or a group will start sending requests to a particular server, and they will do it so quickly that the computer can't handle it, and it's called a denial of service, and the 504s start showing up. How many of you got 504s yesterday? Did you see 504s? Yeah, that means something is it's just hitting that server so hard, the server can't process the requests. And so the requests time out. And generally, gamers like to do it to the game servers. You know, there's somebody gets mad at a particular company, like the people behind World of Warcraft and all that, and they'll try to do denial of service. It gets you in hot water. I will warn you, that is an FBI kind of thing. So you do have to be careful about that if you're a hacker. But other than that, I don't know if that was the case or not, but if you want to get scared sometimes, there are websites out there that monitor attacks, and a lot of them come from Eastern Europe, and they just like to attack mainframes. It could have been somebody dug up a CenturyLink cable too, or a Verizon cable. Sometimes that happens, and that can knock out your internet. So just be aware that there are reasons why those things happen, and sometimes those are signals from God that says go out and play in the leaves. Come back and do it later. It's not your fault. You're not doing anything wrong. It's the network. We'll just blame the network because that works. That works for everybody. All right. I guess I should be using this. I still don't know how to use this right. Come on, turn off. There we go. All right. Anybody, before we move on, is there any other technical kind of questions you have you're having issues with? This is a good time to ask before the weekend. I think it's okay. All right, well, let's go on to this content question I got. You probably weren't alone. I don't think this gentleman who asked this question was alone. But on one of the questions on the homework, the handout homework, it was to draw what iron and sulfur might look like as a mixture versus one was a compound. Did y'all see the movie, the iron sulfide being made? Okay, you should have. It was in the Nearpod. All right, so what happens is if you take iron, that's not going to work. There. All right, see how all that works. All right, so you can take iron. And when we're talking about particle diagram, we're just talking about circles and shapes, things that represent elements. And I'm bringing in iron. Why do I know that's an element? If you didn't know anything else about this particle diagram, how could you identify that this was a pure element? It has only iron in it. Is iron attached to anything else? Now let me define attached to you. In a particle diagram, this is what we mean by attached. And if we pull that up, like this, you see how when one goes up, the other goes up with it? And there's a set definite pattern, right? If I were to pull some more iron in, even if I kind of brought it down like that, it's not attached, it's just close. Is this a pure substance now, or is this a mixture? This is a mixture now. All right, so that's what we mean by a particle diagram. So I'm going to pull these out of here. And I'm gonna put my sulfur in here now. So now we have a mixture of iron and sulfur. And I got a little bit fancy, I filled it in with my computer. On the draw it slides, we found out the hard way, it doesn't work that well. So you may wanna do like a solid dot and an open dot, and just leave it alone like that. Or you can make a black dot and a yellow dot, because you have color options. So you could do something like that. Now, according to the video, how could you separate out this mixture? What did they use? They used a magnet, because iron is magnetic. And they pulled all of it out, and they were smart. I was never that smart when I did this demonstration, because I would just stick the magnet in there, and then I'd have iron filings stuck permanently. They were smart. They at least put something over the magnet so that it could easily get it off of the magnet when they were done. Sulfur, on the other hand, is not magnetic. That's what we mean by a difference between a mixture and a compound. A mixture is something you can physically separate. Some of your answers on that worksheet were just spot on. If you have a mixture of sand, sugar, and water, or sand, salt, and water, well, can you separate the water from the sand? You sure? Yeah. Sand is a solid, right? Doesn't it? You haven't been to the beach? Water doesn't dissolve sand. So how could I separate the water from the sand? You can filter it. You could just pour it off, and then spread the sand out and just let it dry. That's one way of doing it. But what about sugar and water, or salt and water? Does that filter?
No.
They're soluble. That means they dissolve in the water. Some people said they're the same size as the water. That's not terribly wrong. It's not what's happening, but when you talk about something being dissolved, it means it's mixing with those water molecules. So yeah, I guess on the side of the coin, that could be considered a correct answer. But more specifically, it was dissolved. Now, we all did it. The bane of your mother's existence. You go upstairs with some Powerade or some God. Airplane mode is your friend. Anyway, you go upstairs with a glass. Maybe it's just Kool-Aid. Mom made some Kool-Aid. You got younger brothers and sisters, and she made Kool-Aid. And you said, I'm over Kool-Aid. I'm a teenager, but you know darn well you're gonna grab some. So you went and you grabbed some, and you went upstairs to your room, and you drank about 3 or 4 fourths of it, but there's this little bit left, and you forget about it. Come back in a week, what's left? Nothing, just the residue, all right, just the residue below. So that's kind of an extremely slow process, but that's called evaporation. But if you really wanted to get to the salt or the sugar right away, you just boil the water. And the water will boil off, and the salt or the sugar will lay at the bottom. That is still a physical means. If you were in Dr. Yates's class, in his heyday, when he would do the fermentation, I don't know if he did it last year or not, but he usually makes alcohol down there. He grabs a bunch of apples from the cafeteria, those fruit snacks you used to get with the grapes and the apples and everything in that. They would all contribute that, and they'd make a mash, and then he would do the distillation process. He is 3rd or 4th generation distiller. His father, it was his grandfather's. His grandfather had a corn whiskey that he made that was almost identical. In fact, it had less water in it than Jack Daniels when they tested it. So he knows his stuff when it comes to distilling alcohol. So anyway, so he used to do that with everybody when they were in biology. I don't know if he still does it or not. It's a shame if he doesn't, because it was a lot of fun. All right, so this is a pure substance. This is a mixture. Yeah, another pure substance. And that's what the point of that homework was to get us to identify on the particle level whether something's a mixture or compound. So let's take a look at something like this. This was another thing that they did. What state of matter would these two boxes be? Solids. This one is probably what? Gas. Now a liquid, if it were a liquid, it would be, let's say this was molten. You know how it loses its shape? But it's still kind of to the bottom, isn't it? And still kind of close together. But it has lost, oops, it has lost its crystal shape. In fact, it just flew right out of the beaker. All right. So that would be a liquid state. And which one of these three boxes, 1, 2, or 3, which one is the mixture? 1. Do you see why it's not 3? What is the giveaway that this is a solid, but it's a pure substance?
Because they're all touching.
Yeah, they're all touching. That tells you it's a solid, but what were you saying, Kate?
Because they're all packed in.
Close. That tells you it's a solid. There's a pattern. Thank you, Christina. There's a pattern. Do you see the AB pattern? A, B, A, B, A, B. Does that not fit down here? A, B. In fact, we call this is not a molecule. This is called a formula unit. Ionic compounds, which we're going to be learning about hopefully next week. Ionic compounds are not molecules. Molecules terminate. If you think, for example, H2O. Everybody know what H2O is, right? Okay. H2O is a molecule because when you pack it, it doesn't go on and on and on. If you've been to Bristol Caverns, or any of these other wonderful caverns that are in this area, because most of this area is limestone, and limestone tends to get eaten out pretty well by underground water and rivers and all that sort of thing. But if you go to Bristol Caverns, beautiful, beautiful stalagmites and stalactites, crystal displays, beautiful crystal displays. They get bigger and bigger and bigger because ionic compounds get bigger and bigger and bigger. These are examples over here. I'm trying to find one that I think will show up on the camera. Isn't that pretty? That was grown in class by a student from a few years back. All of those were grown by students. And they can get bigger and bigger the longer they sit. So formula units are just that. It's the unit part of the crystal that has electrical neutrality. But you can have as many of them as you need. A molecule, on the other hand, it's H2O, done. Not going to get any bigger. You can have a lot of those molecules, but those molecules aren't going to grow. So I say they're terminal. They don't get bigger just because you add more stuff to it. You see the difference? Thumbs up if I'm clear. Sometimes I worry. Dr. Hopkins sometimes does not translate well to students, so let me know. All right, so is this okay? Do you understand now what that homework was about? If you haven't finished it, go back. I found out I have a new tool. I discovered something. I can actually type on your homework. So when you go back and look at your submissions, you'll see comments right on the paper. I'm trying to get you so you can see where they're at. If you didn't get fully commented on, it might be because after a few select ones, I realized I needed to bring this up in class. And so you may not have anything in red, but for the most part, unless you were really way off base, you probably got 20 points for it.
Click on your pod.
Where?
Show up.
There's the code up there too.
It's
KDW
under your grades on
39.
the left. Keep going. At the very bottom of your list.
here. I don't think it's case sensitive. They just do it that way so you know exactly what the letters are. All right, so way back in August, we talked about observations, and we talked about quantitative observations and qualitative observations. So, quantitative means what to you? If somebody said, go get me a certain quantity, what are they implying? A number. So quantitative chemistry is means numbers. We're going to be talking about numbers. Qualitative is observation. What you did on Wednesday, observing chemical change, that was observational. Now we're going to talk about quantities. So apples. This is apple season right now. How many of you have you been to the pumpkin patches yet? You know, and the apples and all that. That was my favorite time. When my kids were little in preschool, my favorite little field trips to go with them was the apple orchard and the pumpkin patch. I mean, between the fall colors and how sticky their fingers were getting from eating all of that great candy and all that, it was just a great fun time. So it's appropriate that we should talk about apples right now. Now, are all apples the same? Of course not. You have pie apples. What's the biggest difference between a pie apple and maybe an apple that you would eat? Actually, I would eat any of them. I am not just grown. They're, sorry, what?
Aren't they sweeter?
Not the pie apples.
They're more bitter.
Yeah, they're tart, like Granny Smith's. They have a tartness to them. They're also crisper. They have less water in them. Where a apple like say like a Fuji apples, they have a sweeter taste to them. There was pink ladies are excellent too. Those are wonderful. But you have these different apples, and they vary in sugar content, and they vary in density. Some are very big, some are very small. Crab apples are about maybe yay big, but they're still an apple. So all apples are not the same. So usually when they get sold by weight instead of by volume, because you can make a lot more money if it's by weight. You can be more standard by using weight. So, knowing how to count, knowing how to weigh, and knowing how to measure the volume can all go into how we want to sell our apples. And down here we have what's called a conversion factor. Now I'm going to be talking math lingo. I'm sorry. I know I'm speaking that 4-letter word. But what we're actually going to be talking about in these lessons has less to do with chemistry and a lot more with how we in chemistry use math. I promise it won't be past Algebra 1. It's all going to be in that Algebra 1 level, all right? So your fear of quadratic formulas and limits and integrals, you can relax. We're not going to be doing that. But that's what these are. These are conversion factors. They convert one unit to another. That's what a conversion factor is. 12 inches equals 1 foot. Same distance, right? I didn't change the physical nature of the length, I just changed the unit that I'm talking about. So all these things effectively, numerically equal 1. And that's what a conversion factor does. All it does is change the unit. Now, it's very easy to think, well, you're changing the number. No, I am changing a number, but it's still the physical size. I can call this grams, I could call this ounces, I could call this all kinds of things, but I didn't physically change it. It's still the same thing. So what I'd like you to do is, this is where the paper and pencil comes in, because it's easier to do on paper and pencil, but then you can use your text tool down here, and you can type. What I'd like you to do is to calculate the mass. What is the mass of 90 average sized apples if 1 dozen of the apples has a mass of 2 kilograms? There's your conversion factor right there. 1 dozen apples is 2 kilograms. So go ahead and on your paper, see if you can do that.
Yeah, pencil sharpener.
I do, but it's broken and it's right above Christina's head. Do you need a pencil?
Yeah, I'll say that.
I have them with
Oh, okay. I think I can go back to teacher view. Now, I'll keep your secrets in. We have 90 apples. Can y'all see that in the back? Is it bright enough? What I've written here is we've got 90 apples. Very first thing we need to do is do what? Got to get it to a dozen, because our conversion factor has what 2 units? Dozen and kilograms. So I got to get at least to dozens first. And then once I know the dozens, I can determine the mass. So I'll let you work on that for just about a minute. All right. Most of you are coming up with 15 kilograms. That is correct. Our thought process follows that you had to get to dozen first, so you should have gotten 7.5 dozen, and then multiplied by 2 to give us our kilograms. Is everyone okay with how that was calculated? Okay, y'all seeing how that works? Now, we have what's called dimensional analysis, and I assure you this has nothing to do with chemistry. It is a technique. It is convenient for me, because when you use it, it makes it really fast to grade. But I'm also not opposed to doing it in a way that it works for you, as long as you mark what the final answer is. Stop it. Oh, that's gonna annoy me. All right, so we started off with 90 apples. And that automatically goes over 1 whenever you start with something. And then we're gonna multiply that by 1 dozen is 12 apples. So apples cancel out, and then there's 2.0 kilograms in 1 dozen. Dozens cancel out, and then you're left with kilograms. So that's what we mean by dimensional analysis. You just link everything up together. It's the way your brain processes it anyway. That's what you would think. You'd say, okay, let's get to dozens and then multiply by 2. So it's just putting it on paper the way your brain sees it. Now, if you did it in 2 steps, it doesn't matter to me. Like I said, I don't care. Just circle your answer so I know what it is. Okay. All right, so there we go. You can go through that again at home. Now, does that make sense? Would you expect it to weigh more than 2 kilograms if you had 90 apples? Okay. Ladies and gentlemen, that is what chemistry really is all about. It's common sense. It's taking units that you're just not familiar with, but applying them the same way as the units you are familiar with. And as long as you keep remembering, yeah, 90 apples is gonna weigh more than 12. As long as you keep that in mind, moles is not a difficult concept. But what it is, it's like growing up, I can't even do it because the mask is on, but we used to joke all the time about moles, and we make the little chipmunk face, and you know, kind of, I can't even do it with the mask. See, you don't even know what the joke is. But that is, you're just not used to talking about things that way. But how many of you have Blackbird or Wolf? Do they not talk in strange units up there?
Sometimes.
Sometimes, okay. Don't they talk like in cc's, you know? Or grams, or in bodily fluids, and all kinds of weird things related to medicine? And if you're out in Maupin's class, he talks sometimes in weird units. He switches between English and metric all the time. So it depends on the application. You may be talking in weird units, and it doesn't feel weird to you because that's what you're interested in. What other information could you calculate about those apples? Take about a minute and tell me, what other things could you calculate? Ooh, got some good ones in there. The density, I like that. Like that. Could you sort them by size? We could sort them by size, right? And kind of determine their masses that way, not like we did with the isotopes. When we did the Candium experiment. Volume and color, that's a good one. Mass per apple, we could have done that. We could actually have done the weighted average in addition to the average. All right, very good. Has everybody had a chance to respond? If you have, I'm going to move on, else you can always come back to it in student pace. So basically, what we need is a common unit. I know what's going to happen. This thing's going to scratch, but we'll try. So you can calculate the number of apples in the bushel by setting up information, but we need that common unit. Because even if we separated them by size, wouldn't we still have to have the kilogram? Whether it was small apples, medium apples, or large apples, we would still need the kilogram as a common unit between all of them. So, how could you quantify sand in a sandcastle? Apples were easy. You could see apples. You could hold an apple. But now you're out at the beach. We're thinking of those days when we could vacation in peace without a mask on. And you're out at Myrtle Beach or Charleston, South Carolina, and you're sitting out there on Sullivan's Island, and somebody's building a sandcastle. How could you quantify the amount of sand in that sandcastle? There we go. Volume again. Good. Helena, very nice. Yeah, measure the bucket. Make sure that you know what the bucket is, so when you put the sand in it, you know how much is there. Five buckets of sand, okay. Aiden's going to throw some algebra at us. Use the equation for area. Ooh. All right, these are good. Weighing. Weighing seems to be the big answer here. Let's see. Let's find out. You could count. I would love to see that one. Counting the grains of sand. I seem to remember a Bible verse about that.
Yeah.
About numbering the grains of sand. By mass. That definitely is a good one. By volume, though. Volume is excellent. because probably there's a certain amount of water inside of the sand, and that could affect the volume and the weight, for example, that could do that. So these are all ways that we could calculate that sand, by count, by mass, and by volume. Counting one particle, though, is going to be a pain in the butt, isn't it? Maybe if you had a hand microscope with you, you might be able to get it down to a single grain of sand. Boy, that's going to be a pain. You'd be like those microbiologists having to count cells on a slide. So he had to start all over again. They do that. That is a real thing. Microbiologists use counting like that when they're determining white cells and all that good stuff. So counting one particle is not going to be practical. Is that more practical? Okay, so we could use a dozen. Chemists use a mole. It is often referred to as the chemist dozen. 6.02 times 10 to the 23rd. October 23rd is mole day. Usually Mrs. Chanley celebrates mole day with her Chem 2s. They make those little stuffed moles, don't you see, and all that. But 10 to the 23rd, it's sort of the chemist version of Pi Day. And it celebrates the mole. But that number right there is the representative number of particles that equal 1 mole, just like 12 eggs are a dozen. And we call that Avogadro's number. Now, Avogadro did not discover 6.02 times 10 to the 23rd. This is a 20th century discovery. It was early in the 20th century. It was named after Avogadro because it was his hypothesis that allowed students in graduate school to figure this out. So he got the, it's more honorary than it is realistic that he came up with it. But we talk about representative particles. And a representative particle, well, in our example with the apple, what was the representative particle? Which one of the, what all of this was representative? We were counting what? Well, apples. We were counting apples. Okay, so a representative particle in chemistry, what is the smallest unit of matter we could have that lets you know that this is a substance? Ultimate particle, thought to be indivisible. The atom, right. The atom is the smallest unit we can have. And if that atom should gain or lose an electron, it could become an ion. You could have a formula unit. And you can have a molecule. And if you want to get really crazy, you can have DCHS cheerleaders. Anything, 6.02 of anything is 1 mole. And there's a reading I used to give PWC, I don't know if I read it for you guys or not, about the mole. Have you had so many moles?
I don't think so.
How thick a layer of actual moles that would be. I'll have to read it for you. I'll wait till next week though. All right, so there. So those are your representative particles. So, know those. I want, hear that, virtual kids? Know these elements. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. These are what we call diatomic, stop it. Diatomic elements. They are pure substances. They are the elemental form, but they exist as 2 atoms combined. That's technically a molecule. But because they are not different, then we say that they are an element. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, it will come back and be a wonderful thing when we are actually writing formulas, if you can remember their diatomic. And when we're doing chemical reactions and balancing equations, it'll be much easier on you if we could do that. So make sure you know that. So those are representative particles. But then everything else usually exists as just the single element. These are examples of molecular compounds: SO2, sulfur dioxide, there's water, hydrogen peroxide, H2O2, very common. I'm gonna skip that. All right, so here's some examples. Copper, the chemical formula is Cu. Its represented particle is generally the atom. You have nitrogen again, and this is atomic nitrogen versus elemental nitrogen. Sometimes you have to explain that when you're dealing, if we're talking about oxygen in the air, for example, that's O2. If I'm talking about oxygen in a chemical reaction, it may be the atomic level, the single O. So it kind of depends on the context. Water is a molecule. Here's an example again of an ion. Calcium group 2 has 2 valence electrons and loses none. And here we have a formula unit. We call this an ionic compound because there's a metal and a non-metal. And we'll get more into that next week. But if every one of these, if you had 1 mole of them, you would have exactly 6.02 times 10 to the 23rd. Now, one of the reasons I kind of compromised a little bit. I wanted our chemistry to be in line with what Mrs. Chanley does. Mrs. Chanley does gases after talking about moles. And I fought that for a long time. I felt you should do gases first because Avogadro's hypothesis comes from the gas laws that says if you have 1 mole of any gas, it's the same number of particles. And that's where these grad students determined that number from. It was from his hypothesis. So for right now, is it okay? Can you just believe me right now until we do gas laws? And then you'll see why. It doesn't matter how much air you have. If you have the same volume of any air, it's going to be the exact same pressure and the exact same number of particles. Okay. All right, and we do the same thing like we did with the apples. We have a conversion factor. 1 mole is equal to 6.02 times 10 to the 23rd. So let's do this. You got magnesium. Magnesium is a light metal. And we're going to determine how many moles of magnesium are in these many atoms. So let's write this down. Let's write our knowns down. We have magnesium, Mg. We have 1.25 times 10 to the 23rd atoms. Now, guys, here's a trick to this. When you're dealing with Avogadro's number, you can, those fancy calculators, you can key in times 10 to the 23rd, no problem. But if you want to do something quick and dirty in your head, think of this thing as like, as Peter Griffin would used to call it, shoulder guy. He's just going to be sitting right over here. He gets carried along for the ride. And generally, if you just focus in on this part of the number, that helps a lot. But we want to know how many moles this is going to be. And we know that 1 mole is equal to 6.02 times 10 to the 23rd atoms. Now this is what I mean. For approximation, just look at the front number for a minute. Okay? I want to keep this as common sense as possible. I don't want you to get lost. Don't get lost in the weeds here. Is 1.25 greater or less than 6? It's a lot less, isn't it? So common sense time. Are we going to have a full dozen or less than a dozen? We're going to have less. So our mole is equal to 6, but we have, what, 1.25. So we don't even have half of this, do we? So when we get our answer, do we expect our answer to be greater than 1 or less than 1? It's got to be less, right? So going back to those eggs again, if 1 dozen is 12 and I only have 6, that's half a dozen or 0.5. So whatever we calculate has to be less than 1. Does everybody agree with that? Give me a thumbs up if you agree with that. Don't get lost in the weeds. Don't get lost in these big numbers. Focus in on the front numbers. So go ahead and set it up. You can use dimensional analysis or you can use what works for you. And let's see what you come up with. I've seen the correct answer. If you're getting anywhere around 0.2, you are correct. What happened to the 10 to the 23rd when you did the division? It disappeared, didn't it? It just disappeared. So just don't get overwrought about this. Now this is 0.2 times 10 to the 23rd, or would have been, sorry, forget that, we got rid of it. But what if this was, instead of 1.25, it was 0.125 times 10 to the 23rd? If you wanted to put it in proper scientific notation, you would have to move your decimal up, and then this would go from 23 to, I think, 22. So just be aware there are some games you can play with your decimals, but for the most part, I don't care. If you just want to totally scrap that 10 to the 23rd when you're using these calculations, going back and forth, I'm okay. Unless you're giving me the actual particle number. Is everyone okay? Thumbs up. Anyone having difficulty on the calculation? You took the 1.25, you divided it by 6. That's how we got it. So 1 mole, 6.02. There it is, the 3 significant figures. By the way, guys, on any test bank questions I have, 3 significant figures is the magic digit number when you're doing calculations. All right, so here we have propane. Hank Hill. Propane is a gas used for cooking and heating. How many atoms? So we're going the other way now. We're going to take 2.12 moles of propane. And let's, again, always write your knowns down, your givens. We're going to take our, what's on here? 2.12 moles propane. And we know that there are 6.02 times 10 to the 23rd atoms. Oh, this is a little tougher. Okay, atoms. Let's do this first. Before you do atoms, do molecules. Let's just do molecules first, because that's not an atom, is it? C3H8, that's a molecule. So let's just do it as molecules first, and then we'll take it from there. This is a little more complicated than I thought it was. So this is molecules equals 1 mole, because molecule is a representative particle. All right, now it's a little easier to set up. So now before you're doing calculations, common sense time. 1 mole is 6, right? But you have more than 1. How many do you have? 2. You have at least 2. So this answer should be somewhere around 12, shouldn't it? Okay? So whatever your answer is coming up with, you should be getting close to 12. All right? So let's go ahead and set up the dimensional analysis. And again, shoulder guys, just coming along for the ride. So you're going to get, what is it? It's 12 point what? 12.7, close enough. Times 10 to the 23rd. Now again, if you want to put it in proper scientific notation, you could move that decimal point over, but if you just left it for me like that, I'm so easy, guys. All I care about is that you know how to do this. Math class, they're going to want you to do though. If you're within a couple digits of any of my answers, I usually give you full credit. Okay, so 12.7 times 10 to the 23rd, and that's molecules. Are we okay there? Is that okay? Okay. Because we're going to take it one more step. You don't have, if you're talking about atoms, now, you have C3H8. How you read that is there are 3 atoms of carbon, 8 atoms of hydrogen, and that equals 1 molecule of propane. That's what we mean by a chemical formula. It tells us exactly how many atoms are in a molecule. So what is the total number of atoms in this molecule? Should be 11, right? So there are 11 atoms in 1 molecule. That should give us a whole new conversion factor, right? So I have the number of molecules, 12.7, right? And each molecule has 11 atoms, so let's we've got that part figured out. I have 12.7 times 10 to the 23rd molecules. And I can multiply that by one more conversion factor. There are 11 atoms in 1 molecule. So what do I have to do now to get my total number?
Multiply.
Just got to multiply by 11. So what, 12 times 12 is 144, so what's 11?
I'm at 139.7.
139.7. And again, you can always rewrite that 1 potato, 2 potato, 1.40 times 10 to the 25th. If you want to put it in proper scientific notation. So not a big leap, right? It's not a big leap. All righty, very good. So go ahead and answer the question real quick. How is a mole similar to a dozen? And while you finish that, I want to take a real quick look at this Megamole cheat sheet. Right now, all we've talked about is going from moles to particles. We've just done this top part right here. So for now, you can complete this Nearpod in student paste at home over the weekend. You got 2 days. But if you're going to do the Megamole worksheet, I'm not going to make this due on Monday. I'll give you a day or 2 past that. But right now, I just want you to do the examples where you're going from representative particles to moles. Don't do the mass ones yet until we have had time to look at them in class. So this second page where they're going, moles to atoms is fine, but as soon as they get into grams, stop there. So you'll go basically to this example right here. So, yeah, stop here for Monday. I don't want you to get ahead. Someone should stay with me. So virtual kids, you too. You're going to just stay within representative particles and moles. Yeah, everybody got that? Understand the assignment? I do want you to complete the Nearpod, get it done. It'll go into grams and moles and all that, but we're gonna go over it again on Monday. So even if you feel like, oh, I still don't understand this, that's okay. But if you do that, if you go through it ahead of time, you will be in better shape on Monday, because even if you didn't fully get it on the weekend, come Monday when I talk about it, it'll be like, oh, that's what that was. All right, that's what I'm hoping for. So again, keep it always centered. Put a dozen eggs in front of you to just remind you, this is a mole. That's what a mole is, it's just a dozen. So Friday, okay, we want to finish this. Now, y'all remember, student pays, there is an actual page. You click, opens it up full screen for you. Don't go through the Nearpod, that's just for life. You want to, let's save the CK12. And I'll fix that on the agenda. Save that one for Monday, because that goes into all the different representative particles as well. But complete megamole for representative particles only. In other words, times 10 to the 23rd.
Does that mean we don't worry about the first one about the people dot for CK?
Correct.
Okay.
Because that one, it's all moles, but it's everything. Now, if you want to go ahead and look at it, the questions really aren't hard. But until we have a chance to talk about mass per mole and volume per mole, there's really just no point in confusing you on your own. I'd rather you listen in class first, and then I'll turn you loose on it. We are going to be doing percent composition, but I think when you see, you add up the masses, that's your total mass. You go back to your individual masses, you divide them by the total mass, you get percent. It's really very easy concept. So we'll get into that next week and all as well, but let's make those changes in the homework, and that should actually simplify things a little bit for you.